Hello, I welcome you all in this course on mechanical measurement systems, and today we will discuss the flow visualization. Flow visualization is important because we don't have analytical techniques to find the flow field in a system where the fluid flow is taking place. So, in absence of these analytical techniques, some experimental techniques are used. And if we use experimental techniques where interference with the flow is taking place, then it will change the flow field. So there are certain techniques, and these techniques are optical techniques of flow visualization, right? So today we'll start with shadowgraph, then we'll discuss the Shell-Reen, interferometer, and then LDA, laser Doppler anemometer. So these four techniques we'll be discussing in this chapter, in this lecture. First of all, we'll discuss about the flow visualization, how the visualization of flow is done. For example, there is a channel, or the fluid is flowing perpendicular to this board. So there is a channel. Right, and across the channel there is a glass window, right, and a pencil of light is entering from this side, or a ray of light is entering from this side and going through this channel, and there is a uniform, there is no density variation inside this channel. When there is no density variation, without deviation, this pencil of light will pass through this test section, and here y is equal to y1, and this is y direction, and this is x direction. Now suppose there is a variation in density. When there is a variation in density, this ray of light will be deflected, right? And this is known as epsilon deflection angle. And deflection angle can be expressed as epsilon is equal to lambda by n1 dn by dy, y is equal to y1. N is the refractive index, n1 is the refractive index, right? And lambda is the wavelength, okay, wavelength of the light. And it is equal to L beta by rho s. Rho s is the density of the surrounding fluid. d rho by dy, y is equal to y1, because the change in the refractive index d rho by dy, okay. So a derivative of refractive index with respect to y is equal to the derivative of density with respect to y, because this change in the refractive index is a function of change in density of the media. Here beta is a constant, dimensionless constant, and beta is equal to 0.292 for air. It also varies from one fluid to another fluid. For air, it is 0.00292, right? And this is the angle of deflection, epsilon. L, this is the L length. I think rest of the values are with us. We don't know this d rho by dy, right? Now, these are the basics which are used for flow visualization techniques, in the flow visualization techniques. Let us start with the shadowgraph. Now, in shadowgraph, let us take the same test section. There is a viewing window, right? And the ray of parallel lights, parallel rays of light is entering this channel, and there is no variation in the density, then they will simply pass through this, right? Suppose there is a change in the density of the media here, and if there is a change in the density of the medium, then these lines will tend to converge or diverge depending upon the change in density. So instead of getting lights like this, let us, this is the y plane, some of the rays may converge and some of them may diverge, and we will be getting not uniform illumination on this side, some dark spot and bright, depending upon the change in the density, whether density has increased or density has decreased. Now this variation in the figure is in the image is known as the shadow graph, and very good example is of shadow graph. This process of this shadow graph is when you take a hot plate. When hot plate is heated, there is a variation in density from the surface of the plate to the top. So the air which is in contact with the surface of the plate is at lower density. Air, when you are moving up, the density is gradually increasing. If you look just at the level of, if you keep your eyes at the level of the hot plate, you will find you can see the convection currents. With the naked eye you cannot see, but if you put your eyes just at the level of the plate, you can see convection current moving us. That is also a sort of shadowgraphy. I mean, that is a very, a primitive or a crude type of shadowgraphy, but this is also how I can explain you the shadow graph. So the hot plate, when you are looking at the hot plate at the at your eye level, then when you are seeing the convective current, so that is a one type of shadowgraphy, and shadowgraphy has many applications in the fluid flow, especially where there is a change in density. For example, there is a shock wave. If there is a shock wave, then through shadowgraphy we can see the movement of the fluid or the flow visualization or disturbance in the flow due to the shock waves. So that is one technique of flow visualization. Now the illumination in the shadow graph, it depends upon the change in deviation or epsilon with respect to y. Higher is the change, more is the contrast between dark and the bright spots, or better visualization is there, and this change is equal to the second derivative of density with respect to y. Now after shadow graph, I will take up the shell ring. Shell ring is a very popular and reliable technique for flow visualization, or SCHLIEREN, shell ring. So this is a very popular technique of flow visualization. In case of shell ring, there is an object. Let us assume there is an object AB, right? And this object is the ray of light which is coming from this object is passed through a convex lens. So there are two rays. They are coming to L1, lens 1, right? After coming to the lens 1, and this is our visual section, and fluid flow is perpendicular to this board. So this is visual section, and after this lens, it goes. The ray it crosses in the middle of the test section, and they cross each other, and come out of the test section, and then they pass through another lens, L2. This is L1 and this one is L2. So they will also cross each other and they will come to L2. Right? Now after L2 there is a image formation, and this is a plane 2, this is plane 1. So plane 2 you can draw with different color. This is plane 2. And this is a lens. And after this lens, because they are passing through this lens, they will change this path and they will cross each other at plane 2 and form a, now the form an image. Now the plane 2 will come here. When they cross each other, then plane 2 will come here. So plane 2 will come here. They will cross each other here, and the plane 2 will come here. Right? And this is plane 2. And plane 2, because this is AB, so this is real image A dash, B dash. Then again it will go to another lens, that is L3. And after L3 they will converge and form a image. Suppose this image is CD, then this will be C dash, D dash. So arrangement is, optical arrangement is more or less like this. I'm repeating. Now there is an object, suppose there are two sources, not an object, there are two sources A and B. They are starting from here. After going through a lens, they are converging at plane C and D. Right? And the image of plane C and D is formed on screen in the form of C dash and D dash, right? Using two lenses, further two lenses. Now we can easily see, and visualize the fluid flow. Now there is a change. Now there is a change in the density of the fluid. That is one thing. Second thing is, if I put a knife edge here, if I put a knife edge here, some of the rays will be obstructed and this image will become faint. I will amplify the knife edge here. It is going to be like this. There is a knife edge, right? This is your B dash and A dash image, B dash and A dash, right? And this B dash and A dash is partially covered with the knife, and the part of the B dash A dash above the knife edge is Y1, right? Now when we are putting the knife edge, this image is becoming faint. Now there is a change in the density in the flow field. When there is a change in the density in the flow field, then the deviation of the rays will take place. The deviation of the rays will take place. Those who are straight, due to change in the density, they will be deviated from the path. And this knife edge will be obstructing the rays, those rays also which it is not supposed to obstruct, because a ray which was passing over the knife edge, now it will be obstructed by the knife edge, right? Or this is also possible, the ray which was earlier obstructed by the knife edge will go over the knife edge. In fact, the presence of the knife edge will create contrast here, contrast in the image. And this contrast is further, and this contrast in the image will further enhance the visualization of flow. It will further enhance the visualization flow inside this channel, right? If we want to do certain mathematical analysis, then this delta y is equal to F2 epsilon. Epsilon is the angle and F2 is the focal length of this length, of this lens F2. And contrast can be defined as, the contrast on the screen can be defined as the ratio of it is a ratio of the, or it is a fractional change in illumination with general illumination. So contrast is the fractional change in illumination. Contrast is high means fractional change in illumination is high. It may be on the darker side or it may be on the brighter side, or it is going to be delta y over y. Okay, and then delta y over y1. Sorry, delta y over y1. It will depend upon this, right? And that is going to be equal to F2 epsilon divided by y1. Earlier we have written one equation. If you remember, earlier we have written one equation that epsilon is equal to lambda by n1 dn by dy is y is equal to y1, right? And we have also written n is equal to 1 plus beta rho by rho s n1, right? Now making use of this, right? Making use of this, we can write the contrast as I'll rub this off, it is not required. So we can write the contrast as C is equal to F2 L beta divided by y1 rho s, it is density of the surrounding, d rho by dy at CD. CD I have rubbed off, yes, that is CD somewhere here. It was the plane in the test section. So this will give the, mathematically we can write this, the contrast like this, but the Schellrin, it has, I mean, just I have described you the working principle of Schellrin. Otherwise there is a lot of optics and the electronics involved nowadays, and we have very sophisticated instruments which used Schellrin and do the flow visualization, and flow visualization can be seen on the computer screen. So after Schellrin, we will take up the interferometer. This is another optical technique of flow visualization, that is interferometer. Now interferometer works on the principle that, first of all, if there is a change in density, the path, there is a splitter. I will start with the diagram, then I will explain it. Okay. So there is a light source, and light source, the light goes to a lens, and this is lens L1, and then there is a splitter. Now this is a normal optical technique. Then through a splitter we have two rays, and then these two rays will recombine. If they are traveling the same path, then there will be no interference, so no fringes. But if there is a difference in the path due to change in the density in the path, then there are going to be the fringes, and n lambda is equal to difference in the path travelled by two rays, or delta x is equal to n lambda. So same techniques will be adopting here. There is a splitter. So a splitter will split the rays in two parts. One part of the ray will pass through the splitter. Another part of the ray will be reflected by the splitter. Right? Now after this there is a mirror. On the mirror the ray will be reflected and it will pass through the flow field. There is a flow field. So it will pass through the flow field. After passing through the flow field, again there is a splitter, and here also there is a mirror. So they will be reflected by the mirror, and this is S2, and they will pass through S2, and there is a lens. They will pass through lens, and then there is a screen, and this lens is L2. So this is the entire diagram or entire arrangement of interferometer. The light rays starting from here, they will move in this direction. Then part of the rays will go here, will pass through the splitter. Part of the rays will be reflected, and then there is a mirror, and there is a mirror here also. This is M2 and this is M1, and the rays will be reflected. They will be passing through the flow field, and after passing through the flow field, again they will go to the splitter, lens, and then screen. Now suppose the density is same in the entire system. So I mean there is no difference in the path travelled by two waves, right? Suppose there is a change in density here. That will change. That will create delta L, path travelled by the light by two methods or two routes, and delta L is equal to L n minus NO, that is change in the refractive index. And delta L, if you remember the equation, that n is equal to 1 plus beta rho by rho s n1. So n minus NO is going to be equal to, or we can take delta L as beta L rho minus rho O divided by rho s. That is, beta is already with us for different, it is a constant, and it is a unique value for a particular fluid. For air, I have already written the value of beta. L is known, L is the length of the flow field, right? Rho minus rho O by rho s. So this is going to be the value of delta L, and n is equal to number of fringes is equal to delta L upon lambda. So this is also divided by lambda, and this is also divided by lambda. This will give the number of fringes. So this is how this technique can be used for flow visualization, interferometer. And the last one is LDA, laser Doppler anemometer. It also adopts the same technique. First of all, creating a path difference by virtue of density, change the density in the flow field, and then due to when the path difference is created, then the fringes will be developed, right? So we'll start with the LDA, laser Doppler anemometer, and it is also known LDA, laser Doppler anemometer. It is also known LDA. In laser Doppler anemometer, as it is clear from the name, it's a laser is used, right? So suppose there is a pipe, there is a flow in the pipe, right? And there is a transparent visual section in the pipe, right? And in transparent visual section, a laser is shot. So there is a laser, and laser will pass through this section, right? Due to change in density, part of the laser will be deflected in this direction, theta. There is an angle theta. Then there are lenses. Lenses are everywhere in optical methods. So there is a lens here. This is L1, and there is a lens here, that is L2, and this is a lens here, L3. So laser is coming from this side, and after scattering from here, so it should have some particles or sometimes artificial particles are also injected to have scattering, right? So this deflection is due to scattering from the particles. And suppose we take tap water. Tap water has sufficient particles for the purpose of scattering. So we don't have to add some artificially some particles in the flow field, but sometimes they are required to be. If there are no particles for the scattering, then the LDA type of system will not work. So laser will come to the pipe. Due to scattering, the particles will be scattered at angle theta. Through lenses, there is a neutral density filter. Neutral density filter is there. Then they will come to the mirror. There is a mirror, and from mirror, then again there is a beam splitter. There is a mirror. From mirror, it is coming to the beam splitter, and from beam splitter, and this beam will also come to the beam splitter. Now, beam splitter will send these signals to the photo amplifier. There is a photo amplifier. Photo amplifier, the purpose of the photo amplifier is to enhance the signals, right? When the signals are enhanced by photo amplifier, then they go to the electronic processing unit and then display, right? This is the basic arrangement for LDA, and LDA can have different type of arrangement. This is one of the arrangement, and the basic purpose is after scattering, when the scattering takes place, these two rays, they recombine, and there is a photoelectric amplifier which amplifies the signals, and since there are number of particles right, in the flow field, so this theta will also keep on changing. It will not remain constant, right? So, and this is how we get the picture of entire flow field inside a tube. But it is on the point-to-point basis. This is all for today for the flow visualization. Thank you very much.